In the world of solid objects, occupying the same space at the same time is a recipe for destruction. Physical matter must deform, bounce, or shatter because two bodies cannot inhabit the same coordinates simultaneously. Wave mechanics follow a different set of rules. On this stretched string, we have two distinct pulses on a collision course, one displacing the medium upward and the other pulling it downward. At the precise moment they overlap, the string snaps into a perfectly flat, motionless line. The pulses appear to have completely annihilated one another. Yet an instant later, they emerge on the other side. They continue their original paths at their original speeds, with their shapes entirely unchanged by the encounter. This raises a fundamental question. If the waves didn't destroy each other during that moment of absolute stillness, where did that energy go? This behavior occurs because a wave is a series of traveling instructions. It is energy moving through a medium, like this string, telling every individual particle exactly how far to move from its resting position. When two sets of instructions arrive at the same place at the same time, they follow the principle of superposition. This rule states the net displacement is the algebraic sum of the individual displacements. If we freeze the overlap, we can measure the displacement at a single point. Here, y1 instructs the string upward, while y2 instructs it downward. The string adds them. The positive and negative values result in zero net displacement. This happens at every overlapping point. Each push is countered by an equal pull, creating a flat line. The annihilation we saw earlier was actually a moment of perfect mathematical balance. The waves never truly touched. Their instructions simply summed to zero. This principle applies to continuous, repeating harmonic waves just as easily as single pulses. Here, we have two identical sinusoidal waves flowing through the same medium. The combined waveform is determined by the phase difference, or phi. This measures how the peaks and troughs of both waves align with one another. When the phase difference is zero, the waves are perfectly synchronized. Every peak in wave 1 sits directly above a peak in wave 2. Because the peaks align, their values add together to create a wave twice the size. We call this constructive interference. If we shift the alignment by 180 degrees, the crest of the first wave now aligns with the trough of the second. The positive and negative values cancel out perfectly across the entire medium, resulting in total silence. This is destructive interference. The difference between a massive signal and total silence is determined solely by the geometric alignment of those peaks and valleys. During total destructive interference, the medium shows no movement at all. It is tempting to assume the energy has vanished. But the underlying reality is different. Even when the string is motionless, the individual waves are still actively traversing the medium. The string is effectively a messenger caught between two equal and opposite sets of commands. It stands still because it is being told to move in two directions at once with equal intensity. This highlights the independence of waves. Unlike physical objects that are permanently altered by impact, waves are independent entities that pass through one another without losing their identity. The principle of superposition shows that what looks like a collision is actually a temporary mathematical combination. This algebraic addition is the foundation for noise-canceling technology and the resonance of musical instruments. When waves meet, their displacements combine according to these precise geometric rules.